Good day, esteemed researchers and curious minds tuning in from around the globe. We're diving into the fascinating world of scientific language models with our paper, Galactica, a large language model for science. We explore how these models, specifically our Galactica, can revolutionize the way we interact with scientific knowledge, overcoming limitations of current methods, and potentially disrupting the traditional store and retrieve paradigm. Stay tuned as we delve into this groundbreaking research and its intriguing implications. The traditional way of accessing scientific knowledge has been through a store and retrieve paradigm. This approach, while effective, has led to a significant bottleneck as the reasoning, combining, and organization of information still heavily relies on human effort. Language models, on the other hand, have shown impressive capabilities in absorbing technical knowledge, such as LaTeX equations and chemical reactions. However, despite their strengths, current language models still need an architectural change to perform tasks like humans. They are not yet capable of performing tasks that require adaptive computation, such as step-by-step reasoning. To address these challenges, we propose using language models as a new tool for exploring scientific literature and knowledge. We've demonstrated that these models can compose a curated knowledge base to perform well in knowledge-intensive question-answering tasks. We've also introduced a working memory token approach, which has shown strong performance on mathematical MMLU and math benchmarks. This approach allows the model to handle complex tasks that require reasoning and organization of information. Our research has led to several key results that highlight the potential of language models in scientific applications. Firstly, we found that language models can surpass retrieval pipelines in predicting citations. This suggests that they could be a valuable tool for exploring scientific literature in the future. Secondly, we discovered that language models can effectively compose a curated knowledge base, which is particularly useful for tasks that require intensive knowledge, such as question answering. Lastly, our models demonstrated the ability to learn tasks like IUPAC naming through self-supervision. This opens up exciting possibilities for their use in fields like chemistry, where such naming conventions are crucial. Let's delve into the traditional method of accessing scientific knowledge. This method has been dominant for over half a century, but it's not without its limitations. It heavily relies on human effort to reason, combine, and organize information. This reliance has led to a significant bottleneck in knowledge throughput. The image you see here, titled Model-Machine Symbiosis, illustrates our approach to address this issue. We're exploring how language models can disrupt this paradigm and bring about a new interface for humanity to interact with knowledge. This could potentially alleviate the bottleneck and enhance our ability to access and utilize scientific knowledge. Language models are poised to disrupt the traditional paradigm of accessing scientific knowledge. Our work aims to provide a new interface for humanity to interact with knowledge. These models have shown an impressive ability to absorb technical knowledge, such as LaTeX equations and chemical reactions. However, the current store and retrieve paradigm still requires significant human effort. While language models are making strides, they still need architectural changes to perform tasks like humans. Our proposed method involves using language models to explore knowledge. This represents a significant shift from the traditional approach and offers a potential solution to existing problems. We're excited to delve into this new frontier of knowledge exploration. The current bottleneck in knowledge tasks is the availability of high-quality step-by-step datasets. However, we believe that increasing the number and size of these datasets can significantly boost performance. To improve the problem setting, we've employed a working memory token approach, which has shown strong performance on mathematical MMLU and math benchmarks. Now, let's talk about the potential of large language models, or LLMs. These models can act as a bridge between scientific modalities and natural language, marking a key improvement in the field. By effectively bridging this gap, we can unlock new possibilities and push the boundaries of what's achievable in scientific research. Our research introduces a new approach to accessing scientific knowledge, disrupting the traditional store and retrieve paradigm. We leverage language models to explore knowledge, offering a fresh perspective on how we interact with information. Our proposed method utilizes a working memory token approach, achieving impressive results on MMLU and math benchmarks. We also delve into the potential of large language models, or LLMs. These models can act as a bridge between scientific modalities and natural language, opening up new interfaces for knowledge interaction. One such model is Galactica. It's capable of learning tasks like IUPAC naming through self-supervision and has been trained on diverse datasets, including PubChem compound, UniProt, and RefSec genome. This demonstrates the versatility and potential of language models in scientific knowledge exploration. Our research introduces a novel training process that employs data augmentation techniques. We use order randomization and format randomization to ensure a balanced learning experience between natural sequences and natural language. This approach allows the model to learn from different perspectives, enhancing its understanding and performance. In terms of performance evaluation, we've tested our model on a variety of benchmarks and tasks. These include citation prediction, knowledge-intensive question answering, and automatic protein annotation. Notably, our model outperforms tuned sparse and dense retrieval pipelines in the task of citation prediction. This demonstrates the model's ability to absorb and utilize technical knowledge effectively, providing a valuable tool for exploring scientific literature. Our model exhibits impressive capabilities. It can compose a curated knowledge base, performing well in knowledge-intensive tasks. It also achieves strong results without the need for direct fine-tuning. However, we've identified a current bottleneck: the availability of high-quality step-by-step datasets. This limitation can hinder the model's performance. Looking ahead, we see potential improvements. By increasing the number and size of datasets that bridge between natural language and natural sequences, we can further boost the model's performance. This approach opens up exciting possibilities for future research and applications. Our research has yielded some key technical results. We found that language models can effectively absorb technical knowledge, even outperforming retrieval pipelines in citation prediction. They can also compose a curated knowledge base for knowledge-intensive tasks. For instance, our model, Galactica, learned tasks like IUPAC naming through self-supervision. We also saw potential for tasks such as automatic protein annotation. These results have significant implications. Language models can take on tasks currently done by humans, suggesting a promising future for these models in scientific research. They can understand and generate complex scientific nomenclature, which opens up potential for automation in biological research. These findings underscore the transformative potential of language models in the scientific domain. Let's take a look at this illustration, which showcases Galactica's ability to attend to functional groups. This is a key aspect of the IUPAC naming task, where the model focuses on the part of the molecular graph associated with the group name at each prediction stage. Now, let's summarize our findings. We've explored how language models can disrupt the traditional store and retrieve paradigm. These models, like Galactica, absorb technical knowledge effectively and use a working memory token approach to perform strongly on MMLU and math benchmarks. We've also seen the potential of large language models as a bridge between scientific modalities and natural language. Galactica learns tasks like IUPAC naming through self-supervision and achieves strong results without direct fine-tuning. Finally, our research shows that language models can outperform tuned sparse and dense retrieval pipelines for citation prediction and perform well in knowledge-intensive question-answering tasks. This is a promising direction for future research. Our research has revealed some key takeaways. Firstly, language models show immense potential to undertake knowledge tasks that are traditionally the domain of human specialists. This opens up exciting possibilities for the future of knowledge management and exploration. Secondly, we've identified that the current bottleneck in this field is the availability of high-quality, step-by-step datasets. By addressing this, we can further enhance the capabilities of these models. Thirdly, we've found that increasing the number and size of datasets that bridge between natural language and natural sequences can significantly boost performance. This suggests a promising direction for future research. Lastly, our work indicates a strong potential for language models to disrupt the traditional store and retrieve paradigm, paving the way for a new, more efficient interface for accessing knowledge.